Welcome back, Marauders. This video 17.4 is about solubility equilibria. So when you have a salt in a solution, some of the salt will dissolve. So imagine this is a container of water and then we drop a chunk of salt in it, let's say calcium fluoride, which is a solid. Well, some of the calcium fluoride will dissolve and you'll make calcium ions and fluoride ions. And eventually it'll reach an equilibrium. If you put enough salt in there, eventually it'll reach its saturation point and no more salt can dissolve. And you'll have an equilibrium established between the aqueous ions in the solution and the solid down at the bottom. So it's a saturated solution. It's holding as many ions as possible. And so when this happens, you have the solid as your reactant and then the dissolved ions, and an equilibrium is established. So we have a two-way arrow because every time the ions go down and become the solid turns back into the ions, and the concentration of the ions stays the same in the saturated solution at that temperature. So here's the equation for calcium fluoride. Calcium fluoride solid makes calcium ions that are aqueous and 2 fluoride ions that are aqueous. And so since this is an equilibrium, we can write an equilibrium expression for it. So K is equal to, we always put our products on top. So the concentration of our products, calcium ions times fluoride ions. And then since the fluoride ion has a coefficient of 2 in front, we'll square that. And then on the bottom, we don't need to include the reactant because it's a solid, and solids don't get included in equilibrium expressions. So this is the equilibrium expression. It has a special name. It's called KSP, which stands for solubility product. And so there's constants that you can look up in books and tables where you'll find the solubility product constant for various salts. And the size of this constant tells you it tells you how soluble the salt is. So if it's a big number, it means you produce a lot of products. If it's a small number, it means you produce very little product. So the bigger the KSP value, the more soluble the salt in general. Let's look at Okay, so lithium carbonate has a solubility of 5.48 grams per liter, and we want to find the KSP, the solubility product constant. So we'll write an equation first. We have lithium carbonate, which is a solid, establishing an equilibrium with lithium ions that are aqueous and carbonate ions, which are also aqueous, and then there'll be a 2 right here. So with that equation, we can write out the equilibrium expression. So KSP is equal to, we have our lithium ions, and that concentration will be squared because of the 2 in front. And then we have the carbonate ions. So we need to figure out the concentration of lithium and the concentration of carbonate, and then we'll plug it into this equation and we can solve for KSP. So we have 5.48 grams of Li2CO3 in every liter of solution. And so we'll multiply this by the molar mass, so 1 mole of Li2CO3 for every, out of the molar mass, 73.8 grams Li2CO3. Okay, and so this will give us moles per liter, or molarity. We want to find it for each ion, so let's look at the ratios here. We know that there's 2 moles of lithium ion produced every time you have 1 mole of Li2CO3. And so the molarity of the lithium ion is going to be 0.148 molar for lithium ion. And then we'll just continue this right here. For the carbonate ion, there's 1 mole of carbonate ion for every 1 mole of Li2CO3. And so the molarity of the carbonate ion is going to be 0.074 molar for CO3 with a -2 charge. Okay, so we have our molarities of our 2 ions. We can plug them back into our equilibrium expression. So KSP is equal to 0.148 is our concentration of the lithium. Don't forget that needs to be squared because in our original equilibrium expression, it's a 2 because of the coefficient. and then times the carbonate concentration 0.074. And so we'll square that, multiply these together, and we'll get the KSB value, which is going to be 0.0016. And so that's the equilibrium constant. It tells us how much product you're going to make compared to how much reactant will be left over. This example is kind of working the other way. So in this example, we're given the KSP value, and we want to try to find the molarity. So it's kind of working backwards compared to the last problem we just did. We'll start out the same way by writing an equation for calcium phosphate dissolving in water. So you have Ca3PO4 2. So that's a solid. And then that will dissolve in water to form 3 calcium ions that are aqueous and 2 phosphate ions with a -3 charge that are aqueous. All right, so that's your equation, and then we can write an equilibrium expression with that. So our equilibrium expression is going to be KSP is equal to concentration of calcium cubed, and then phosphate, and that has a 2, so squared. So that's your equilibrium expression. So for this one, we were given KSP. It told us in the problem that KSP, or you could look that up in a book, KSP is 2 times 10 to the -29. And that's going to be equal to the concentration of calcium cubed times the concentration of phosphate squared. And we want to find these concentrations to find the molarity of that original solution. So we think about this one as an ice table problem. And so we set it up like this with our ice table. We don't really care about the calcium phosphate because it's a solid. We care about these starting out at 0, and then they need to increase. We can see here the ratio is 3 to 2, so we can make this go up by 3x, this go up by 2x. So 3x and 2x are your equilibrium concentrations of the calcium and the phosphate. And so we can plug those values in and we'll solve for x. So for calcium, we have 3x, and then it's cubed because of our equilibrium expression. And then 2x is going to be squared. Okay, so now we just need to use some algebra to solve for x. So we have 2 times 10 to the -29 is equal to 3x cubed is 27x cubed. And then 2x squared is 4x squared. Okay, multiply these together and you get 108x to the 5th. Divide both sides by 108 and we get, and then take the 5th root, and you get that x is equal to 7.1 times 10 to the -7. Okay, so since x is 7.1 times 10 to the -7, that would be the molarity of the calcium phosphate. The molarity of the calcium at equilibrium would be this number times 3, so 2.1 times 10 to the -6. And the molarity of the phosphate would be 1.4 times 10 to the -6. So that'd be the molarity of each ion. But if you're just doing the molarity of the entire salt together, so it'd be 7.1 times 10 to the -7 molar Ca3PO4 2.